Previous lecture, we studied the energy-momentum tensor, which is very important because energy and momentum will curve space and time in general relativity. We have a few more loose ends to tie up with the energy-momentum tensor, and then today we'll start with the dynamics of space and time. Okay, so the loose ends with the energy-momentum tensor. Remember, the energy-momentum tensor has the property that you can express the variation of the action as the energy-momentum tensor times the variation of the metric integrated over. Really what this is saying is, T is basically d of the action by dg. The action, if you differentiate the action with respect to the metric, you get the energy-momentum tensor. Actually, the energy-momentum tensor density. So you have ds by dg, dg by d lambda. It's just a chain rule what is written here, right? So ds by d lambda is ds by dg, dg by d lambda. Okay, now the g mu nu is a symmetric tensor. The t mu nu is not entirely fixed by this equation because if t mu nu had an antisymmetric component, it would be dropping out of that equation. Strictly speaking, mathematically speaking, the antisymmetric part of the energy-momentum tensor is not fixed. In fact, if you derive the energy-momentum tensor the classical mechanics way, for fluid mechanics, usual way, you will see that there is actually an ambiguity in the definition of the energy-momentum tensor. You can add antisymmetric components to it. In general relativity, in principle too, but later on today you will see what fixes it to be symmetric. Okay, so as I said, the energy-momentum tensor is the derivative of the action with respect to the metric, except for a square root of g factor for the measure, and the actual definition is that the energy-momentum tensor is 2 over square root of g times the derivative of the action with respect to the metric. Without this factor of square root of g, it would be what is called a tensor density rather than a tensor. Remember, we found an important equation that holds for the energy-momentum tensor, namely, energy-momentum tensor covariantly contracted with one of its indices is always vanishing. This expressed the diffeomorphism invariance of the theory. Whatever theory of gravity you cook up, the so-defined tensor will always obey that. That's not a law of nature, it's a law of math. If you're going with differential geometry, this follows automatically. It's just the expression of diffeomorphism invariance. And there are 4 equations, because the nu is being summed over. Mu can run from 0 to 3. There are 4 equations, and they correspond to the freedom to choose the 4 coordinates arbitrarily. That's the diffeomorphism invariance of the freedom to choose your coordinate system whichever way you want. So this in itself cannot and is not a conservation law, because in general in space-time we should not expect that there is a conservation law. And that's because conservation laws, we know from Noether's theorem, reflect a symmetry. But general relativity doesn't require space-time to have any symmetries. It doesn't have to have translation or rotational symmetries. So we don't expect conservation laws of energy or momentum or angular momentum. And so this too shouldn't be a conservation law, and it is not. It looks a bit as if it were a divergence, and when a divergence is vanishing, then you have a conservation law, but it's not a divergence because there's this extra index mu. If this was just a contravariant vector whose contraction, covariant contraction, whose contraction with its covariant derivative is vanishing, then we would have a conservation law via Gauss's law, via Gauss's theorem. But we don't. However, still T mu nu plays an important role in terms of energy and momentum, even though it expresses energy momentum, even though energy momentum are generally not conserved. In particular, when there are symmetries in space-time, then we actually do obtain a conservation law from that. Not directly from T mu nu semicolon nu equals 0, but using it together with the symmetry, we obtain a conservation law. Namely, a spacetime possesses a symmetry, or technically an isometry, if so-called killing fields exist, or if one killing field at least exists. And a killing field is a vector field psi for whom the Lie derivative of G is vanishing. The physics of it is that if you do the diffeomorphism, which maps the manifold into itself, which is generated by the infinitesimal flow of psi, then the metric doesn't change. And if the metric doesn't change under a transformation, then you have a symmetry. Technically, this is the equation for finding a killing vector field. Once we have a killing vector field, then we can contract the killing vector field with the energy momentum tensor, and we obtain a vector P mu, which describes a conserved flow. Namely, we then have that P mu, now this is in fact a contravariant vector, contracted semicolon with mu, that is equal to 0, and then by Gauss's theorem, that gives us a conservation law. So notice there's just one index, that means it's a divergence, and therefore, because this is a divergence, you can use Stokes or the special case of Gauss's theorem, and then you can show that the integral over the boundary of that flux is vanishing. We had this in the previous lecture, which is to saying that whatever flows into the box must flow out of the box as well. So we have a conservation law.
Excuse me?
Yep.
So I wonder if the reverse reasoning goes. Suppose I have a P mu that is conservative, but I do not require psi to be killing vector. Then can I infer from the conservation that psi is a killing vector?
That is very interesting. I've not seen that question formulated before. I suppose that may be possible to prove. Intuitively, I would expect this to be true. Give it a shot. I mean, try it. If it's possible to prove, it shouldn't be more than just a few lines. That's very good. Okay, so how many killing vector fields can spacetime possibly have? How about 2, 3, maybe a million? It would be great if it had a lot of killing vector fields, because then we have a lot of conservation laws. And having a lot of conservation laws, a lot of conserved quantities usually helps in solving the equations of motion. It turns out, and we will see later on exactly why it is, that spacetimes can have at most 10 killing vector fields. Intuitively, in fact, it's also exactly, but I'll show you later with the relevant math, a 3 + 1 dimensional spacetime can have at most 10 killing vector fields, 10 independent killing vector fields, because there are at most 4 translation symmetries for the 4 spacetime directions, and there are at most 6 generalized rotational symmetries, the 3 spatial rotations and the 3 boost directions. So in total, at most 10 killing vector fields. Of course, actual spacetime has no killing vector fields, because if anything, we are breaking already translation invariance and rotation invariance by the way that we impact the curvature around us. Now, killing vector fields are important not only for conservation laws, but also to characterize properties, general properties of space-times. You see, I'll make a few comments in the next few slides, where the philosophy behind them is the following. General relativity is a highly nonlinear, complicated theory where much of the ingredients isn't even known. General relativity is going to be a highly nonlinear theory. We will see that later on today. And when I say a lot of its ingredients are not known, I mean that a lot of the matter that curves space and time is not known. We see plenty of matter around, but that's probably only about 3% or so of the energy and mass and energy that's around in the universe. And then the bulk of it is dark matter and dark energy. And we don't know what that's really made of, and what its relationship is, for example, between its energy density and its pressure. But these are important for general relativity. So even though it's a beautiful theory, there are lots of unknowns in there. And therefore, it is often useful to think in general terms, to think, what properties can energy momentum tensors possibly have? We can only calculate the energy momentum tensor exactly once we know all the sources of energy and pressure in the universe, which we don't. So we cannot actually calculate the energy momentum tensor until we know exactly what kinds of matters are around. But we still have to work with energy momentum tensors. So it is good to formulate general categories of energy momentum tensor behavior. And similarly, correspondingly, it is useful to think of categories of space-times. Even though we may not be able to nail down exactly which one we're dealing with, but it's good to know general properties of them. So for example, a space-time, and by that I mean a differentiable manifold with a Riemannian metric, or pseudo-Riemannian metric. A space-time is called stationary if it possesses energy conservation. Which is to say that this is the type of space-time which has a time-like killing vector field. Right? The time-like killing vector field translates into the conservation of the time-like conserved quantity, which is then, by definition, called energy. So this is to say that we call a space-time stationary if there exists a killing vector field, psi, which obeys this condition, that's the killing condition, and where the killing vector field is of negative length, which is to say it's time-like. Which is to say that there's always a coordinate system in which this is a vector which has only a zero component and no space component. Right? A vector would be, with our signature convention, time-like vectors have negative length squared, and light-like vectors have length equals 0, and space-like vectors have positive length squared. Okay, so when we have a time-like killing vector field, then we can always find coordinate systems for which the time-like vector field takes this form. It's basically when you move with that flow that's generated by the psi. Then you are, the flow is then addressed with you. In this case, we have that the killing condition, if we choose the coordinate system to be co-moving with that flow generated by the killing vector field, then let us reconsider the killing vector equation. We know that our psi is not only time-like, it's also killing vector. So that holds, which is to say that this equation holds. But this then means that the so this is vanishing because of the killing condition. We have that the time derivative of the metric is actually vanishing. Which is to say, which is also very intuitive, that if we have a time-like killing vector field, then we have energy conservation, and the symmetry is literally that the metric doesn't depend on time. So there is a coordinate system such that the metric is independent of time. So in this coordinate system, we have that literally the time derivative of the metric tensor's matrix is vanishing. Physically, that means that co-moving observers that flow with the diffeomorphism that's generated by psi, for those observers, the metric doesn't change in time. It doesn't change. The environment, the local environment of curvature is constant in time. See, you can always choose a coordinate system, of course, in which the metric is time-dependent. You just choose a time-dependent change of coordinates. The point here is that there exists a coordinate system in which the metric is not time-dependent. That's a highly non-trivial thing. General metrics don't have coordinate systems in which they are constant in time. Now, you might think that when a metric is static, then automatically it should be possible to write the metric in a coordinate system in which it is simply g naught naught 0 0 0 0 0 0, and all the non-triviality is in the space-space part, so that there's only non-trivial stuff going on in the space-space part. That is not so. You can have spacetimes which are static, so the metric is sort of frozen in time when you express it in a suitable coordinate system, but you can't write the metric in this form yet. That requires something in addition to have that form. So for example, a black hole, a Schwarzschild black hole, a non-rotating, very, very simple black hole, would be a static spacetime, because you can write down the Schwarzschild solution, obviously, in a way such that it doesn't depend on time. And the Schwarzschild solution can also be put in this form, that it's stationary. But when you have a rotating black hole, then that's not so. For a rotating black hole, you can find a coordinate system in which it is time independent, the metric is time independent, but you cannot find a coordinate system in which it takes this form. As you can imagine, for a rotating black hole, stuff is going on, and yet the metric is in suitable coordinates independent of time. So we say that a metric is not only, or a spacetime is not only stationary, but it's also static if the metric can be put into this form. And it turns out that the mathematical condition, there's a mathematically nicer way of saying that the metric can be put in this form. And the mathematically nicer, because coordinate system independent way of writing that is to say that a spacetime is called static if it has a time-like Killing vector field psi, which when viewed as a one form, so we are pulling the index down and it's a one form, it's a covariant vector field, which when viewed as a one form, it obeys the so-called Frobenius condition. So if the Killing vector field is not only time-like but also obeys that condition, then there is always then and only then there is a coordinate system in which the metric takes this form. One direction of this statement is easy to check. If the metric is of this form, sorry, what I wanted to say is that if the metric is, okay, so if we have a time-like Killing vector field, which is of this form, yeah, I don't see it at the moment. In any case, I'm not giving you the complete proof of this statement anyway, but you can prove that this is the condition for such that if and only if that condition holds, the metric takes this form, and then the spacetime is not only stationary, then it is also static. Okay, so this was these were examples of making general statements about classes of spacetimes, being static or being stationary. Similarly, and that's the flip side of the coin, it is very often necessary to make general assumptions about the energy momentum tensor because we are not so sure about the matter content of the universe. So here are some generic properties, not of space-times now, but of energy momentum tensors. And you see, maybe I should highlight that again. The energy and momentum are curving space. And how much they are curving space, for example, whether it's sufficient to generate singularities, we cannot decide because we don't know exactly what kinds of matter are contributing to the energy momentum tensor. Therefore, we put energy momentum tensors into broad categories and we say if the energy momentum tensor turns out to be in this category, then we can go into the Einstein equations and find out what that means for example, for the occurrence of singularities. Okay, so here are two general classes of energy momentum tensors that might occur. The first is the class of energy momentum tensors that is characterized by obeying the so-called weak energy condition. So these are energy momentum tensors for which this inequality holds, where T mu nu is the energy momentum tensor and V is any arbitrary time-like vector. Now that is a huge class of energy momentum tensors, and it's very reasonable to assume that no matter what matter we find in the universe, the energy momentum tensor will obey that condition. The reason is that if V is a time-like vector field, then there is a coordinate system for which this has only a zero component and no space component. So you're flowing with that vector field. In that case, in your coordinate system, this is simply T00. It's just the 0,0 component of the energy momentum tensor, which is the energy density. And so this equation is simply saying that the energy density is assumed to be positive for observers that travel with the flow of V. Another category of energy momentum tensors is obtained by considering the property of the dominant energy condition. So assume that the weak energy condition holds, so that this inequality is true. And in addition, assume that this vector, the contraction of the energy momentum tensor with a time-like vector field, obeys that k mu smaller equal to 0. What's the significance of requiring that? Well, the significance is this. Remember, in general, our space-time doesn't have any killing vector field. If it does have a killing vector field, and V is a killing vector field, then this contraction here is a vector that describes a conserved flow, if V is a killing vector field. So this is the flow of energy and momentum indicated by this time-like vector field, which may or may not be conserved. If V is a killing vector field, that gives us a conserved quantity. It's a divergence-free vector. If V is not a killing vector field, then this still describes the flow of energy and momentum, but it's not conserved. But it's still the flow of energy and momentum, even though it's not conserved. So what we're requiring here is that the energy density is positive, and that makes the weak energy condition hold. And the dominant energy condition requires also that the flows of energy and momentum are such that these flows be they conserved or not, these flows have negative length squared, which is to say that they are time-like, which is to say that they flow in a causal way. So what this dominant energy condition is saying is that, first of all, energy is positive and it may not be conserved, but the flows are at least flowing in a causal way. They're flowing inside or on the light cone. We have that the length is smaller or equal to 0. Right? If K was a flow that is light-like, we would have to have 0. If it is time-like, we would have that it is negative. Otherwise, you see, when we have a flow, in principle, if it's not conserved, it could be leaking space-like, which means it's non-causal flow. Energy disappears here and it reappears somewhere else immediately, faster than the speed of light. That is prevented by that condition here. Okay, so again, that's a very reasonable assumption to make. We can only check the weak energy condition or the dominant energy condition once we know exactly what makes up the matter in the universe. But it's just to say, it's a reasonable assumption that whatever dark matter is, for example, this should come up. Yep.
I just have a question. So the way we defined the energy momentum tensor was purely mathematical. So it was this tensor that verifies the mathematical relation. So I'm not so sure how we can relate it to our intuitive notion of energy. So we can make this motivation.
Yes, right. Okay. So remember how energy and momentum arise ordinarily, before general relativity.
Yes.
Well, they arise as being paired with symmetries.
Yes.
Okay? Noether's theorem. And here, we made a definition which might have looked strange initially. Why would we differentiate the action with respect to the metric? But we did it anyway. We obtained the tensor T mu nu, and then we saw that for every symmetry, for every Killing vector field, we have a conservation law. And so we said, okay, we have this pairing again between symmetries and conservation laws. And then we defined energy as arising from the case of a flow vector, which is time-like, of a Killing vector field that is time-like, and if it's space-like, you get a momentum. So the connection to the usual definition of energy and momentum was that. Basically, the business of Killing vector fields is replacing Noether's theorem. It's a manifestation of Noether's theorem. Okay, so we have this condition here, this additional condition, the weak energy condition, which is saying that the energy density ought to be positive, is supplemented by this condition here that makes it the dominant energy condition. And in an orthonormal basis, the dominant energy condition, this extra condition here, takes this form. Namely that the 0,0 component of the energy momentum tensor, which we know is positive, is larger or equal to the modulus of any space-space components of the energy momentum tensor. Which is to say that, in this sense, the energy dominates over the momentum component. Hence the term dominant energy condition. The energy is dominant in that inequality. So now we are about ready to study the dynamics of space-time. We can calculate the energy momentum tensor explicitly if we are given a particular content of space-time. If it's a perfect fluid, we can do it. We can calculate the energy momentum tensor. If it's a scalar field, we can calculate the energy momentum tensor. If it's an electromagnetic field, we can also calculate the energy momentum tensor. But, well, there's dark matter, which is actually more than the visible matter. So we can't really calculate the bulk of the energy momentum tensor. That's why we considered the weak and the dominant energy conditions. And later on, we will also get a strong energy condition and yet another one. They're all designed to give us a handle on working with general relativity, even though we are not so sure what the energy momentum tensor is. Okay, so now let's calculate the dynamics of space-time. But you had a question, yeah?
Do we distinguish between future and past yet? Because the previous thing said all flows is into the future.
Well, that's right. In principle, that could also be in the past. It's just time like that. You have the square of it. Yes, that's right. So you would have to check that. We will later in this course study the conditions under which general relativity allows travel into the past. In principle, general relativity allows for solutions which have closed time-like loops, and you can associate conditions on the energy momentum tensor to the presence or absence of such closed time-like loops. So the dynamics of space-time, we have the dynamics of fields, right? The Klein-Gordon equation, or geodesics, perfect fluids, and so on. But how does space-time itself move and change in response to the matter that is dynamic in space-time? So here's the action as far as we have it. The action is given by the Lagrangian density multiplied with square root of g, integrated over all of space-time, and the Lagrangian density contains all the matter fields that we know and we don't know of. Dark matter, dark energy, and the visible stuff. All of this has some Lagrangian, some of which we know, some of which we don't know. So, not for dark matter. Now, the equations of motion of matter are obtained, as we discussed last time, by varying the action with respect to the fields psi that go into the action. Remember, psi stands for the collection of all matter fields and radiation fields. For cosmologists, matter and radiation are all called matter. So the equations of motion are obtained in this way. That includes the Dirac equation, it includes the Klein-Gordon equation, the Maxwell equations, and so on. And in practice, this equation translates into that set of differential equations as we derived as well recently. And you notice that the action depends on all the matter fields and on the metric. If we vary the action with respect to the matter fields and set that equal to 0, we obtain the Klein-Gordon equation and the Maxwell equations and so on. So we get the dynamics of matter. Do we get the dynamics of space-time by differentiating the action with respect to g? That would be really nice, right? Take the action, differentiate it with respect to psi, get the matter equations of motion. Differentiate it with respect to g, get the equations of motion of space-time. Let's see if that works. So let's vary the action with respect to the metric, set that equal to 0. What do we get? Well, when we differentiate the action with respect to the metric, we get 1/2 t mu nu square root of g. That's basically the energy momentum tensor, equal to 0. That's not a good equation of motion. It tells us that the energy momentum tensor has to vanish. So we are missing something. That can't be right. That can't be the proper equation of motion for the metric. The universe would have to be empty of matter if this were the correct equation of motion. So in fact, what we are missing is a part of the action. Just like the matter fields each contribute terms to the Lagrangian, also the metric contributes terms to the Lagrangian. It's the Einstein action that we are missing so far. By writing down only the action of matter fields, we're missing the so-called Einstein action contribution to the total action. But then once we have that contribution, then it will work. Then, once we put here the Einstein action as well, then functionally differentiating the action with respect to the metric, setting that equal to 0, will give us the Einstein equation and the proper dynamics of space-time. And we know already one term of the Einstein equation. It's the term that we obtain when we functionally differentiate just the matter action with respect to G. That's just the energy-momentum tensor. The energy-momentum tensor must be there in the Einstein equation. Now, at this point, I could just put up the Einstein equation. I could just put up the action and say, this is it. Trust Einstein, he got it right. But the thing is, what would we have done without Einstein? Would we have ever found general relativity? Now, for sure, we wouldn't have found it so quickly. But the latest, in the 60s, Andrei Sakharov would have found it. And he derived it in a much better way than Einstein did. Einstein was basically ingeniously guessing, checking and rechecking consistency conditions and so on. And he had made some wrong guesses along the way. He published a theory with Fokker in which they had the equivalence principle, but it wasn't quite general relativity, didn't get the right predictions. Now, Sakharov, in the 60s, in one of the shortest papers ever, it's just half a page, had a much better way of explaining where general relativity comes from. Had a much better way of explaining where the extra terms come from that we are missing so far in the action, the Einstein action and so on. Where does that come from? Get a much deeper insight in where that comes from. And so let me explain that. Rather than just flashing the Einstein action, let's derive it along with Sakharov. So Sakharov in 1968 showed that quantum effects of matter induce suitable extra terms in the action. They induce the extra terms that get us general relativity. In other words, general relativity is unavoidable. It's because quantum effects will generate just the right kind of terms in the action. Now here's Sakharov's reasoning in a somewhat modernized language. Sakharov considered the difference between a classical and a quantum theory. Don't even think about gravity just yet. Just think about a classical and its quantum analog systems. If you have a classical system, then it's described by some action, and the equations of motion are obtained by varying with respect to the degrees of freedom, setting that variation equal to 0. So this could be the action of, Klein-Gordon fields, for example. But as you know, that is not really exactly true in nature, because in nature everything is quantum. And that, in effect, changes the evolution of the system. It doesn't completely behave as the same way that the classical system does. Let me highlight that. It's very important. You may be spoiled by having dealt with harmonic oscillators too much. See, usually we approximate everything with harmonic oscillators, and then we say the higher orders are too difficult. But harmonic oscillators are very, very peculiar. Harmonic oscillators have the feature that the dynamics of the quantum expectation values is exactly the same as the dynamics of the classical positions and momenta. This is a coincidence. It basically only holds true for free particle and quadratic Hamiltonians such as the harmonic oscillator. For them it is true that the quantum expectation value has the same dynamics as the classical theory. But every actual system will have some nonlinearity in it, and nonlinearities spoil that. Then the quantum expectation values are having a different dynamics from what the classical degrees of freedom have. How can we understand that there is a different dynamics for the expectation values of a quantum system than what the degrees of freedom of the classical system would do? Well, it's basically because in a quantum theory, not just the extremal evolution of the degrees of freedom contributes. No, in a quantum theory, in the path integral view, all possible evolutions are possible. The sum of all paths, it's a Feynman path integral, and the extremal path, the path of extremal action, can be shown by the stationary phase approximation of oscillatory integrals to contribute most, but still, this is just an approximation. The stationary phase is just an approximation, and in truth, all paths contribute, not just the extremal path. And so, I actually wrote down the equation here. In quantum theory, what we have is that every possible evolution of the fields, of the classical degrees of freedom psi, is associated with an action, and for the action you get a probability amplitude. So every evolution of the degrees of freedom of a system is possible. It has a certain probability amplitude given by this expression. And then you can calculate what is the most likely evolution, and the most likely evolution is the one where the phase is stationary, because in all other cases you have a strong cancellation of these rapidly oscillating complex phases. But there will be corrections in the quantum theory, because not only the extremal paths contribute, but also the neighboring paths contribute. The upshot of this is that when you have a system that's a bit more complicated than a harmonic oscillator, then the evolution of the expectation values of the degrees of freedom is not going to be exactly like the evolution of the classical degrees of freedom. In other words, the equations of motion for the expectation value, for the quantum expectation values, are not going to be exactly the same as the equations of motion of the classical theory. Now, if the equations of motion are different for the classical degrees of freedom and for the quantum expectation values, if the equations of motion are different, it means that they must derive from different Hamiltonians or different actions in effect. So what you have is that the evolution of a quantum expectation value doesn't follow the classical equations of motion, and you have in effect some corrections to the classical equations of motion. You have in effect some correction terms to the Hamiltonian that governs the evolution. This is the method of the effective action. I'm expanding on this here for you to read in black. You arrive at the concept of the effective action, which is far more general than just applicable to gravity. The effective action does the following. If you have a classical system, it has its classical actions. Now you can calculate a quantum effective action for this classical action, from this classical action. And what does the quantum effective action do? It looks just like an ordinary action. You can calculate from it Euler-Lagrange equations. You can solve the Euler-Lagrange equations. And then you get a dynamics of degrees of freedom. It is the dynamics of the expectation values, of the quantum expectation values. Okay? Remember, we just said that the quantum expectation values generally have a different evolution than the classical degrees of freedom. And this new quantum corrected evolution is governed by a quantum effective action. The quantum effective action is almost the same as the classical action, but it has additional terms, which you can calculate in the quantum theory. And they will make sure that if you then treat the effective action as if it were a classical action, you would get the right dynamics of the quantum expectation values. This method is being used in particle physics even when there's no gravity involved. The effective action is simply a very efficient way of capturing the impact of quantum fluctuations. How is the motion of degrees of freedom impacted by quantum fluctuations? Well, you calculate the effective action. And then treat the effective action as if it were a classical action. Calculate the equations of motion and find the dynamics. And it will be the dynamics of the quantum expectation values. In general, you have to calculate the quantum effective action perturbatively. These calculations are difficult, but a lot of effort has gone into this, and good methods are available. So now, Sakharov said, let us do this calculation. That was the content of his half-page paper in the 1960s. In the 1960s, effective action was already known. And he said, let us calculate the effective action for matter fields when curvature is present. Now, it turned out that this can be done, but infinities will arise. I mean, those of you who have done quantum field theory already will know that when you do perturbative calculations in quantum field theory, you will find that there are divergences. In order to get finite answers, you have to regulate those divergences. This is usually considered to be a mathematical trick. And then eventually, as you are done with your calculations, you remove that regulator. That's the process of renormalization. Sakharov said, well, let's just put such a regulator in there. Let's assume that there are no lengths shorter than a length scale LC, L cutoff. You see, the divergences in quantum field theory arise because particles can get too close to each other. The force between them, or the potential between them, diverges. And if you integrate that up too much, then you get infinities. If you assume that there is a finite minimum length in nature, then particles cannot get any closer than this, and therefore what used to be divergences becomes finite. So Sakharov said, well, let's assume that there is a finite minimum length. We don't know at what scale it might be, but let's call that length scale LC. Obviously, it must be much smaller than what we see with microscopes or accelerators. And then he said, okay, let's consider what the effective action is for the matter fields that we are dealing with. And then he said, okay, we start out with the action of just the matter fields. Klein-Gordon field, electromagnetism, and all of that. It's a classical theory. And then he said, consider the quantum field theory of that. Then what is the quantum effective action? What is the action that incorporates the quantum effects for the matter fields? What is the action which, when treated classically, gives you a dynamics which is the dynamics of the quantum expectation values? On very general grounds, not just applicable to gravity or particle physics, the effective action will contain, and that was Sakharov's central point, the effective action that you obtain from a classical action will always be the classical action plus all kinds of terms that are compatible with the symmetries of your theory. In our case, we start out with the Lagrangian here of matter. The Lagrangian that we've dealt with up until this point in this course. It's Lagrangian of matter, and of course correspondingly the action, the effective action, the action of matter. And then when we calculate the quantum corrections to that, we get matter quantum effects. So if there was no curvature in space-time, these terms here that I will talk about in a moment would all be absent. And on flat space-time, on Minkowski space, this is all there would be. We have the matter action that we start with, then we calculate Feynman diagrams and loop corrections and so on, quantum effects, and then we get extra terms in the action. And these extra terms, together with the old action, give you the quantum effective action, which when treated classically gives you equations of motion that describe the dynamics of the quantum expectation values. But remember the general feature of the process of going from a classical to a quantum effective action. The general feature is that the extra terms that arise are all possible terms that are compatible with the symmetries of the theory. And if you work on a general curved space-time, then these additional terms are all possible. You could have a constant here. It's just a number times the identity multiplied with square root of g. That's definitely a possibility. It's compatible with the symmetries of the theory. It is a covariant quantity. So we should expect that the quantum corrections to the evolution of the matter fields will produce a term like this. Let's call it C1. Then there's the Riemann scalar. It's a scalar term. H2 is compatible with the symmetries of the theory because it's just a scalar quantity. And together with this volume form, it integrates well. It is compatible. And then there could be higher order terms which are higher order in the curvature tensor. You know, products of the curvature tensor with covariant derivatives of the curvature tensor, contracted with the metric in such a way that you get a scalar over here. Many possibilities. So Sakharov said that no matter what the matter action is, when we then calculate the quantum effective action that arises from it, it will be the original matter action plus matter corrections that we would have even on flat space, plus all those terms that are also compatible with covariance. And then he said, how big is C1 going to be? How big is C2? How big is C3?
Excuse me.
Yep.
Are there interaction terms between matter and gravity?
Yes. I'm counting them here, though. I shouldn't really write R squared, but in principle, you're right. There could also be terms where you have a Riemann scalar, for example, multiplied with a Klein-Gordon field, or Klein-Gordon field squared. Such things can arise. That's right. I'm not putting them in here. I'm just bunching them together with that.
So in his derivation, he counted those terms?
No.
He didn't?
No, he didn't either. We will later in the course get back to those because there's an issue with conformal symmetry that has to do with the absence or presence of such terms. Okay, so Sakharov's observation was initially quantum fluctuations of space and time, not of space and time, quantum fluctuations of just matter fields will produce extra terms here in the quantum effective action. And then he wondered what might C1, C2, C3, etc. be. Now the constant C1 and C2 will depend, of course, on the actual matter action. It will depend on what kinds of fields, physical fields, are in there. Bosons and fermions tend to contribute with opposite signs, for example, to the constant C1. Bosons tend to make C1 very large. Fermions tend to make C1 very small, contribute negatively. If, for example, we had complete supersymmetry in the matter action, then this would come out to be 0, the C1. But we don't have supersymmetry in nature, at least as far as we know, at least not exact, so this is not going to be cancelled. So the exact values of C1, C2, C3 depend on what kinds of matter fields we have. But you can make a scaling analysis of it. So Sakharov said, well, let's see, C1 should come out to be a constant lambda 1 times the cutoff length to the -4th power. Now where is that coming from? Okay, so see, this constant here must have units. Because the whole thing, the action, is unitless. I mean, in multiples of h bar, it is unitless. So here we have 4 length powers. So this must have minus 4 length powers. So therefore, the constant C1 should be of the form of some number times length to the minus 4th power. It's divergent. And remember, that's quite okay, because we know that these things would come out infinite in quantum field theory if we didn't impose a cutoff on lengths in quantum field theory. And not knowing anything particular about the matter action, we expect that this prefactor lambda 1 is roughly of order 1. Something like pi squared over 7 or whatever it might be. But there's nothing that would allow this thing to be as big as a billion, because there's no number 10 to the 9 occurring anywhere in the action there. So this should come out to be some trivial prefactors of order 1, roughly, times this scaling factor here. Now, what about C2? This constant C2 has different units from the constant C1. This has units 1 over length to the 4th power, to make up for the length to the 4th power here. But R, the curvature tensor, the Ricci scalar, has itself units of 1 over length squared, because it has up to second derivatives of the metric in it. Which means that C2 has only to make up for 2 powers of the integration. So the units of C2 are 1 over length squared, not 1 over length to the 4th power. And so Savarov argued that C2 should be some number of order 1 times L to the minus 2, the cutoff length to the power minus 2. And then it goes on like that. The further you go on the right in the effective action, the larger are going to be the powers of LC. So in L3, for example, if you have R squared here, then there's no power to be made up for, and C3 is unitless, and then higher order terms. Okay, so what we have is that these constants, C1 to C4, etc., have this scaling behavior. Some number of order 1 times this scaling factor, number of order 1 times that scaling factor, and so on. What exactly that number is depends on your model of dark matter and the standard model. But we don't need to worry about it. It's going to be generally of order 1. And the lambda 1s are unitless numbers. The lambda I are unitless because all the units are in these scaling factors. And from that scaling analysis, Savarov deduced that C1 we should expect to be much larger than C2, should expect to be much larger than C3, and so on. You see, LC, the cutoff length, is very small. The assumption here is that there's the smallest length in nature, at least technically it's imposed at the moment. And so LC is a very small length, so to the minus 4th power is a very large number. So C1 is very large. This is still a large number. That is not so large, and so on. So what we see is that we indeed have an expansion here. We have that the effective action has, in principle, infinitely many terms, because there's infinitely many terms that are compatible, that are scalar, that you can add, that you can write down here. But the first one is going to be the dominant contribution, and then this term is going to be the next big, and then that's the next big, and so on, just on the basis of scaling expectations. So let's consider just the lowest order terms in this expansion. The 2 lowest order terms are, other than the effective action of the matter fields, we have C1, which is later going to be identified with the negative of the cosmological constant. And this term here, the second induced term here, is actually the Einstein action. This is what Einstein also wrote down. And the next terms are already much smaller. So at this point, Sarov was quite happy because he had shown that quantum effects of matter fields induce these as the dominant corrections, and these terms are actually the action that produce the correct dynamics of space and time. So he said, great, now we no longer have a trivial action. Now we have the action of matter with the quantum corrections, but that's fine because really matter has quantum corrections. Plus, we have these extra terms and the other ones he was neglecting, and I said, let us now calculate the Euler-Lagrange equations that follow from differentiating that action with respect to the metric and setting it equal to 0. Remember, before we had the quantum effective action, before we added these terms, that equation was simply saying that the energy momentum tensor is equal to 0. But now we have those extra terms. Now it's going to say the energy momentum tensor is equal to something, namely to the derivative of these terms with respect to the metric. Okay, so Sarov at this point had already derived the Einstein action up to these two constants, which he couldn't fix. Well, not yet anyway. By the way, if you want to see a modern review of Sarov's derivation, here it is. It's a paper by Matt Visser in New Zealand. So what then are the equations of motion for G? So in principle, we are now in the same territory as what Einstein did. We have exactly the same form of an action.
I'm a bit confused as to how we're comparing the sizes of these terms, because the coefficients in front don't have the same units. So you have to compare the entire terms, right?
No, wait. The lambdas have the same units because they're unitless. And all the units are contained in here. You see, that's the key. We are assuming that because the action doesn't have tremendous numbers in it, like a billion or so, like the standard model action has only numbers as extreme as like the fine structure constant, which is basically 1 over 137. It's the most extreme number that arises in the standard model. Therefore, and these are the only numbers that go into the calculation of the quantum effective action. So we expect that these numbers here, these dimensionless quantities, come out to be of order 1, maybe order 2, something like this. So, I mean, order of 10 to the 2 at most. And all the other scaling behavior is captured by the scaling powers with the units. And from that assumption, namely that the prefactors are of order 1, and that the rest scales as the units dictate, we have then the relative sizes of these quantities.
But if we wrote the cutoff length in units where it's greater than 1.
Oh yeah, well, well, remember that in that expansion here, oh actually, yeah, in that expansion, all the terms have units of action. So if you measure everything as multiples of h bar, it's unitless, and you're really comparing the size of actual numbers.
Right, so, which is why I said you have to compare the entire terms with each other, rather than just C1 or C2.
You would also need
that
R
is true.
much bigger than LC squared or something.
Sorry?
You'd also need that R is not comparable to C.
Yes, well that's right, yes. We're assuming that R, the curvature is small, it's not getting out of hand. In principle, you could have that the R is making other terms blow up there, that's right. But if R is small, then R squared is even smaller and so on, and so it doesn't destroy our hierarchy of the size of the terms. If R was very large, it could destroy the hierarchy, that's right. And that is the reason why at the Planck scale, where we assume that R can be very, very large, or close to singularities, where R would be very, very large, we really have no idea how gravity couples to matter. We only know how gravity couples to matter, or matter couples to gravity when R is small, where the first few terms are the only ones that matter, where it's only general relativity that contributes.
But R also has units. So how exactly is this comparison working out? It sounds like
Oh, yeah, but
assuming that C2 times R is much less than C1 in magnitude. Right?
yes, it will be. Yes, but that's automatic because we are assuming here that R is, it's the same R here than there and in the higher powers.
Right.
And if that is small, then it means that this term is contributing more than the square, than the third power, than the fourth power.
What does small mean, is what I'm saying.
Well, okay, that
R
is...
in dimensions.
Yes, that is relative to the cutoff. That's right. So again, that's saying that if we are looking at physics close to the cutoff, then that argument is no longer true. That's right. Because then we can no longer say, as you say, that this is smaller than that. This is all, you see, in practice, as long as we are talking about general relativity, as used for everyday cosmology and astrophysics, this is extremely small. And it's extremely close, it's extremely extremely good approximation that this term is much smaller, is much larger than the term with the squared and so on. We have absolutely no experimental evidence for higher order terms there. We expect them to be there, but nobody has found any way of finding them experimentally. It would be fantastic if we could, but don't see them. Okay, so now let's calculate the equations of motion for the metric. So we take the quantum effective action, we differentiate it with respect to the metric. And what do we get? Well, we get now two terms. We get what we obtain when we differentiate the old part of the action, just the matter part of the action with respect to the metric, we get the energy momentum tensor. When we differentiate the new part of the action, namely this part, C1 plus C2 R mu G mu. Remember, that was the Ricci scalar. So what I'm saying is that now we're differentiating, this is the total action. If we differentiate L of matter with respect to the metric, we get the energy momentum tensor. If we differentiate those two new terms in the action with respect to the metric, then, so if we have to differentiate with respect to the metric, then two new terms here in the effective action. There will be higher order terms, but as I said, there is no physical evidence for them yet. So we know this part, we still have to evaluate that part. So we have to differentiate with respect to the metric C1 times the square root of G. We have to differentiate with respect to the metric the product of those two terms, well, and the square root of G. Now that's a little bit of a tedious calculation. I wrote up all details, but let's not spend too much time on that. Let me just give you the gist of it, the outcome of it. Namely, you see, all of this is the calculation that goes into this. Yeah, still proving. Oh my God. Wow. I wasn't aware that it was so many pages. Right. Okay, so what we obtain is that when we do the variation, this particular tensor comes up. And that we call the Einstein tensor, if you remember. So when we differentiate these terms with respect to the metric, this tensor comes up. And putting together the previous pages where the derivatives of the various terms were calculated, A, B, and C, we then obtain that when we differentiate with respect to the metric, the new terms, the two new terms in the action, the constant term plus the lowest order term, C2 times the Ricci scalar, then after all these pages of calculations, we obtain that derivative, completely straightforwardly but tediously, is this expression. Okay, so it is C1 times 1/2 G mu minus C2 times the Einstein tensor. And that is going to be the left-hand side of the Euler-Lagrange equation. The right-hand side was the energy-momentum tensor. So we can conclude that when we take now the full action, either as guessed correctly by Einstein or as derived by Sakharov, and differentiate it with respect to the metric, then we obtain this equation here. The energy-momentum tensor on the right-hand side, and this expression, which is only in terms of the curvature, on the left-hand side. And you see the constants C1 and C2 having been carried forward in all those calculations. When we spell out what the Einstein tensor is again, then we obtain that, and also we divide by square root of g, which we can do because it's a non-degenerate metric. Then we obtain that the Einstein equation takes this form. Here, this is the g mu nu, this is the Einstein tensor, and then if we put this term on the right-hand side, sorry, I've only moved it as far as here, equal to the energy-momentum tensor. Eventually, we will move this term entirely over here to the energy-momentum tensor. But then we have here the Einstein equation, and Sakharov was not able to fix on theoretical grounds what the constant C1 and C2 are. And especially, well, okay, but here this prefactor in front of the energy momentum tensor, C2, he was able to fix. Because the Einstein equation, as Einstein derived it, had a particular value for this here. And that particular value is 1 over 16 pi g, as confirmed by experiments. So this then allowed Sakharov to fix what his number C2 is. Just comparison with Einstein's equation of motion, which was this. Einstein called this his biggest blunder when he kept it, and so Einstein assumed that C1 is 0, so he didn't have that term. And Einstein had that term, and he knew from comparison with experiment that this number, 1 over 2c2, had to be this, 1 over 16 pi g. For Sakharov, this was great because it allowed him to fix what the number c2 is. But if you know what c2 is, you can fix the rest, as we'll do in a moment. So here's Einstein's equation, with c2 fixed as by Einstein. And then there is still this term left over from the derivation of Sakharov. That will be the cosmological constant. You see that in principle it arises on the left-hand side, but it is usually written on the right-hand side as a contribution to the energy-momentum tensor, where it is then called dark energy. So if you put that to the right-hand side, it contributes to the energy-momentum tensor. But how big is that number, 8 pi g C1? Well, Sakharov was able to estimate it. You see, Sakharov predicted that Einstein didn't quite get it right, that he had this term correct, but this term that Einstein dropped, Sakharov is predicting is there. Quantum fluctuations of fields are generating that term. How big is it? Oh, and by the way, the quantum fluctuations of fields are generating that term, and it will contribute, if you write it on the right-hand side, to the energy momentum. Why? What's the physics behind that? And the physics is easy. Well, not easy, but the intuition is clear. You see, quantum fluctuations of fields mean that the harmonic oscillators in quantum fields have ground state energies of 1/2 h bar omega. And if you sum them all up, they contribute this. this term here is the contribution to the energy momentum tensor that arises from the ground state energy and momentum of the harmonic oscillator modes of quantum fields. So it's perfectly reasonable to expect that this term is there. Okay, so Zaharov said, we know what C2 is from comparison with Einstein's equation. So we can find out what the cutoff scale is, LC. C 1 over 16 pi g has to be C2, and C2 was lambda 2 times LC to the power minus 2, where lambda 2 is some number of order 1. So you can calculate what the cutoff length is that gives us the Einstein action correctly. And it turns out to be this number here. Cutoff length LC has to be 1.616 times 10 to the minus 35 meters. That is the famous Planck length. So what Zaharov found is that if in nature there is a shortest length, LC, then the quantum fluctuations of fields generate the Einstein action with the correct prefactor. The correct prefactor here arises from the entire, this term here, the relation, the size, first of all, this arises from quantum fluctuations of fields, and the relative size of the T mu nu and that term, so this prefactor, comes out right if you assume that there is a finite minimum length in nature, which is given by the Planck length. Okay, so LC is 10 to the minus 35 meters. And the order of 10 to the minus 35 meters. But once we have that, we can now calculate what C1 is. See, if LC is 10 to the minus 35 meters, then C1, remember, was some number of order 1 times LC to the power minus 4. So now we can calculate what the expectation is for the size of the cosmological constant. In other words, we can calculate what the expectation is for the energy momentum contribution of quantum fields quantum fields ground state energy, the 1/2 h bar omega of every harmonic oscillator of a quantum field. Simply by putting in here the 10 to the minus 35 meters and taking this to the 4th power, and here we have something of order 1. And you see how this is giving us really large numbers. Because LC is 10 to the minus 35 meters. 10 to the minus 35 meters, but we have it to the negative 4th power. Okay, so it's to the positive 10 to the, in units of meters, we get 10 to the 35 times 4. Times something of order 1. Now, the cosmological constant term is actually given by this expression here. It also has an 8 pi g in it, and if you work it all out, you find that the cosmological constant comes out by Zaharov's method to be 10 to the 70 inverse meter squared. This is the expectation from quantum field theory. The quantum fluctuations contribute a constant term to the energy momentum tensor, and that constant term has this size in units of meters, for example. Now, this is the worst physical prediction ever, because you can also measure that. You see, there's a reason why Einstein dropped the cosmological constant. There was no evidence for it. There was absolutely no physical evidence for cosmological constant. And when he calculated the perihelion shift of Mercury and the deflection of light passing the sun, he didn't need a cosmological constant to get those calculations right. So he said, probably 0. I get the right answer even without a cosmological constant. And indeed, measurements have now shown that the cosmological constant is not 0, but it also doesn't have the value that Zaharov would predict, or that quantum field theory would predict. No, the cosmological constant that we seem to be observing now on the basis of the observation that the universe expansion is actually accelerating. It's a cosmological constant that can do that, make the universe accelerate, as we will see later on in this course. Yes, so the experimental data indicate that the cosmological constant is about this big, 10 to the minus 52 inverse meters squared.
There seemed to be an inherent problem in Sarar's method for computing C1, because he used C to assume C1 is 0, and then he used that to compute C1.
Well, that is true. He used C, you can put it this way. You can say he fixed C2 at experiment, and then derived what his C1 had to be, and then found, and then arrived at a conclusion which invalidates his entire argument, because the first term is so huge.
Yeah, but C2 that he got from the experiment was from Einstein's experiment,
Yes.
which assumes C1 is 0.
That's right. Yes, I completely agree. You know, it's invalidating the thing, because what the experiment is showing is that the cosmological constant is really extremely small, 10 to the minus 52, instead of what Sarov was predicting, which is plus 10 to the 70. Okay, that's huge. It's 122 orders of magnitude off. So even if we allow that, you know, those constants lambda that we were dealing with, where are they? Oh, here, right? We were saying that those constants here that arise in the effective action are numbers of order 1, and then the scaling here, right? Yeah, maybe they are not of order 1, maybe they're of order 100, maybe order 1000. Granted, we still have a problem, because we are off by 122 orders of magnitude. So what this is all boiling down to is that the ratio between the theoretical expectation for the cosmological constant and the actually observed cosmological constant is about 122 orders of magnitude. Now, there's no point arguing with this value that's measured, but the theoretical expectation is also on very solid grounds. The reason why we are expecting a contribution from quantum fluctuations of fields to the energy momentum tensor is that quantum fields really do fluctuate. We really observe that. For example, when we, and just to drive home how severe that problem is, you might say, well, maybe quantum fields fluctuate in the experiments that we do in the lab, but how do we know that quantum fields really fluctuate all the way down to the Planck scale? And only if we assume that quantum fields fluctuate and therefore have non-trivial expectation values of energy, of ground state energy, all the way down to wavelengths as small as the Planck lengths, only then do we have this huge discrepancy. So if we were to assume that quantum fields only fluctuate at really long wavelengths, then maybe that's okay, because then they don't produce that much vacuum energy. So the more modes, the more wavelengths you have that quantum fluctuate, the more ground state energy they contribute. But then look at an experiment that tests for quantum fluctuations of fields, such as the Casimir effect. Are you all familiar with the Casimir effect? Who's not familiar with the Casimir effect? Okay, a few. So let me tell you a little bit about it. Imagine, that's actually the last slide anyway. Imagine in the ocean 2 ships. All right. So the 2 ships are parked next to each other, and there are waves all around. This is in the ocean. The 2 captains know each other and say hi. So they drive up to another and they say hi. Has happened many times. Once I traveled in Italy between two islands, and the two ferries crossed each other, they actually stopped. And, and the crew started chatting with another, and then they went on. Anyway, so you have two ships in the ocean, and there are waves coming from all directions, in the middle of the ocean, right? Then what will happen? Well, an observation that has been made by sailors thousands and, no, not thousands, hundreds of years ago already, is that the two boats will drift towards each other. Right. Well, you see, a ship that's alone in the ocean will be hit by waves from the left and from the right, and about equally. So each time when a wave hits, it'll get a kick in the other direction. But then, on average, there are as many waves kicking it from the right as from the left. So on average, it's jittering left and right, but it's not going to move. But when two ships are close to each other, then there are more waves outside than inside. So they are going to be hit harder from the outside than from the inside, and there's a net pressure, therefore, that makes the ships approach each other. And sailors have to be careful with this. Now, it's very similar when you have not two ships, but two pieces of metal in vacuum. The vacuum has fluctuations, quantum fluctuations of fields. The topic of my course next term, by the way. So quantum fluctuations of fields happen all the time everywhere, even just in the vacuum. And now if you take the electromagnetic field with its fluctuations, and you take two little metal ships, and you put them in the vacuum, just suspend them there somehow, then by analogy with the ships in the ocean, you might expect that they attract each other. Just because the quantum fluctuations from the outside should exert more radiation pressure, quantum fluctuation pressure, on these pieces of metal from the outside than from the inside. Technically, all wavelengths are possible to the right, all wavelengths are possible to the left, but in between, the wavelengths are discretized because it's a cavity. So not all wavelengths exist here. And that means that all wavelengths exert the pressure this way, but only a discrete subset of wavelengths is exerting a pressure that way. And that has been measured. You can actually measure the Casimir force between two pieces of metal. Usually, it's simpler to do it with one metal sphere and one metal plate. But in any case, you can calculate these things, measure them. It's a well-measured effect now. So quantum fluctuations exist, and you do this with distances here, delta L, on the order of, can go to 100 nanometers or something like that. And you can measure that with accuracy, like with an accuracy of %. Maybe they're even at 10 to the minus 4 now. So that means that there are quantum fluctuations of fields down to wavelengths of about that size. Now imagine that this is where the LC is. This is where the cutoff is. Are we then compatible? I mean, we've only tested quantum fluctuations in the vacuum, really down to this scale, at least using the Casimir effect. There may be better ways. There may be ways to measure quantum fluctuations of the vacuum to smaller wavelengths. Well, you can go to smaller wavelengths to about 10 nanometers or so, but once you reach a nanometer, then you get the van der Waals forces taking over the Casimir forces. Anyway, there's solid experimental evidence that this is happening. So LC could be like 100 nanometers, 10 nanometers. That's way bigger than 10 to the minus 35. So we should get a much better ratio here. The discrepancy may not be so bad. And yes, it's not so bad if you do it, if you just plug in the numbers. It's much better if you assume that quantum field theory has the usual quantum fluctuations of modes only down to this wavelength. But we're still off by dozens of orders of magnitude. And that's weird, right? Because we are seeing here in this effect that electromagnetic waves are behaving quantum mechanically down to those scales. The modes of the electromagnetic field have vacuum fluctuations with physical impact at those scales. And those vacuum fluctuations are, you know, like the ground state fluctuations of a harmonic oscillator. They should have 1/2 h bar omega each. And if you sum them up, you're still orders of magnitude, dozens of orders of magnitude away from the experimentally confirmed energy density in the universe. So you see, there's an actual experimental contradiction here. That on one hand, we know that the universe doesn't have a large vacuum energy density. It's only 10 to the minus 52 over meter squared. On the other hand, we do know that quantum fields do fluctuate down to scales like this, and the vacuum energy accumulated just by modes down to those scales is already way bigger than the vacuum energy that we observe by checking how fast the universe is expanding, or accelerating its expansion. And that means that for some reason that nobody has understood yet, the energy contained in the 0-point fluctuations of the vacuum, the energy contained in the ground state fluctuations of quantum fields, that energy doesn't seem to gravitate. For sure, the excitations of the quantum fields are gravitating because that's matter. Matter is gravitating. But why would the ground state energy not gravitate? That is not clear. It's the worst prediction ever. But it's also perhaps the greatest opportunity ever, right? Because whenever you have things contradicting each other, then we're bound to learn something. It's one of the biggest challenges. Maybe one of you guys solves it. Yeah.
Isn't there more to worry about with Sakharov's arguments? Because there's no reason to believe that C3, C4, and higher are exactly 0.
That is right. Yes.
Now we're worrying about well-posedness of the equations of motion.
Yes, there are two things here. One is that the higher order curvature terms, on one hand, are going to be in principle non-negligible, but that only happens when you approach the Planck scale. Otherwise, they are very highly suppressed. Just like the first term, the cosmological constant, is enormously amplified, the other terms are enormously suppressed, which is why we are not expecting to see any evidence of those higher order terms, for example, in the cosmic microwave background or any other cosmological observations. On the other hand, yes, you're raising a very important point, which is that the higher order terms in the Einstein action, in the action of gravity, if they are there, R squared terms, R to the third terms, and so on, they pose a huge technical and conceptual problem as a matter of principle, which is that you're no longer having then the Einstein equation being second order in the derivatives. The Einstein equation, as I just wrote it down there, is second order in the derivatives of the metric. If you have higher order terms in the curvature, you get higher order derivatives. And then the Cauchy problem will be different. You can't just, all our laws of nature that we know so far only require all second order in time derivatives. You only need to know the amplitude and the derivative at the initial condition. You can calculate the future. But this predictability is at stake when you have higher order terms in the curvature. And again, that has not been solved. We know that there are special circumstances when the higher order derivatives can cancel out, but we don't know what would enforce that. All right, let's wrap it up. I'm still here for questions if you are interested.